So, welcome everyone to the second day of the limit camp. Today we have Subhojit. He is a BMath second year student, and he will talk about marriage problem. Over to you, Subhojit.
Thank you, Vikram, for the introduction. So, is my voice clear?
Yeah, it's clear.
Uh, my screen is visible, right? Is my screen visible?
Yes.
Sorry, I think. Yeah, go ahead.
Okay, so uh, today we will be discussing about the marriage problem. So the marriage problem is a classical probability problem which deals with optimal decision making. Like you have to make a decision, but you don't want the decision to be very like you have very limited information or you have a limited time frame. So you want the decision to be most accurate or you want the best possible outcome from the decision that you make. But the information that is given to you is very limited. So the motivation for the problem, if you ask me, then you have to host an outdoor party, right? But it's raining today, so you want to host it tomorrow, or maybe you should wait for longer time, right? Because you don't want the rain to disturb the party, and if you host it tomorrow, might be that there is a high chance of raining tomorrow also. But there is also a problem. If you wait for long enough, then the party might get cancelled, right? So you want a perfect time when you think that the it is very low chance of raining today and you host the party at that day. So you have a rain problem, right? Like this. So how likely is it to rain again tomorrow? Let us think about it probabilistically. So suppose that I tell you that it has been raining for every day since the past week, rather than telling you that it has been raining since today, then you have more information, right? And you can predict better what it can happen. Like if you have the rain for continuing for the past week, might be that it has also to rain tomorrow. And if you have it raining today, the same probability might not be there, right? So the probability changes on the basis of information that you take. Like we will be discussing about this problem at last of the lecture. Where like it is a very classical problem known as the Laplace law of succession, where each day is taken to be independent of each other, and then you take out the probability of the raining, given that it has been raining for the past m days, right? So your beliefs evolve with evidence, right? And information changes the beliefs. So today we will see how information or lack of information shapes your decision under uncertainty, and we'll play a fun story and puzzle like information game. So this is a brief structure of today's journey, and moving on. So what is decision making? So you have to make you have to make a choice in uncertainty. That is what is decision making in a simple raw terms, right? Like layman terms, it is that you have to make choice, but there is an uncertainty in the issue. You have very limited information, you can't go back to the previous decisions, and you need to decide quickly. You have a time bound, that is what. So, like, you can think about it. When was the last time you had to make a decision when you are doing all the options that were available to you? Like, you have to choose an ice cream shop, but you don't know which shop is better, or you don't have all the options to try on for a dress, or you have to make a perfect choice for the college. You don't have all the, you don't, you can't try all the options, right? So, that's where you can use this optical ratio. So you remember Shinchan, right? So from the cartoon basics, right? How many of you watch cartoon or something? So you can unmute yourselves and tell me. Like, is there anyone who watched Shinchan or something? I don't think.
Yeah, a
there will be-
lot of hand is there.
Yeah.
Yeah. Okay. Yeah. He's very popular, right? So he's a popular cartoon character. So there is Miss Nanako, who is super pretty, right? And there is a guy named Action Mask. He's a superhero kind of guy. So what happens is Miss Nanako has a right time to age, right time to marry, and she wants to marry. So what she did is she got n people who want to marry her. Line, some are very good like the action mask, and some are really like you don't know how they are. So, but the best person you know is action master, the superhero, right? So you want Miss Nanako to land up on the superhero guy by some means or the other, but you can't change the process or change the lining up of the situation, right? You want it to be fair and justified, but you want it more probabilistically appropriate to Miss Nanako to land up on the superhero guy. So the problem is Miss Nanako has to pick up them, meet them one by one. Like she meets them in a room and in a personal space, and she talks to them one by one, and she has to right away decide that she likes the partner or she doesn't like him or him. So she has to decide right away. So the problem is that if you pick up a person from random and say that yeah you are the best partner for me, then the probability is very low because given that she's pretty, so it is very high probability that it will be n will be very large, and that implies that 1 by n is smaller. So the probability that she gets a best fit, given that she selects a partner randomly, that is uniformly from all the n candidates, is 1 by n, right? And now moving on. So like if n is 100, like if you take an example, for example, if n is 100, then the chance of selection of success to random selection, you select someone randomly from the crowd, then it is 1 by 100. You get the action mask, one person is there, and divided by all the participants, that is 100. So it is a basic probability. So you can try to. So Shinchan now comes up with a super smart plan to help Miss Nanako. So what he does is he says Miss Nanako that you divide the process into three selection steps, like three procedures, and take the selections. So first is the observation phase. Observation phase is you select a particular first R candidates and then remember the best among them, and you reject all of them, the first R candidates. You don't choose the first R, you just reject them. Then you go on to the selection phase. In the selection phase, what you do is you have the first subsequent candidate who is better than the best from the previous observation. That is, you remember the best R, right, in the observation phase, and then you choose the person, the first person who is better than that R, like the best among R. You choose the first person who is better than that R from the continuing subset, right? And by default, if suppose the action mask was among that R person, so what she does is if there is no such candidate who is better than the first R candidates, then you have to by default go to the last one. It's a bad fit, right? So that's how Miss Nanako gets the idea from Shinchan. And now Shinchan is a bit tough to believe on, right? He's a bit notorious and he likes to do mischief, right? So if Miss Nanako rejects the first n by 2 candidates, suppose that n is even, and she rejects the first n by 2 candidates, what happens is she is left with only 50% of the chance of getting a right match among those n by 2, rest of the n by 2, right? You get almost 50% of the chance, like a very low probability. The most of the candidates have been rejected. So what is the ideal R that she must reject so that she gets to the action mask guy optimally, like the best possible R value that is there? So let us define it mathematically. Now suppose I rank them in the following order, that the first one who is there, he is the least priority, or he's the most worst candidate among all of them. And the nth one is the one who is the action master, that is superhero guy. So he is the best among them. Now define a random permutation. So what is a permutation? Is it's a play of word. It's just like you randomly or arrange all of them. Right? You don't know where is n and where is one, or where is the person three, or rank three person is where. You don't know. You land upon a permutation, random permutation. So so now moving on to the probability, like what we can understand from here probabilistically. So before that, we'll develop some theories which will help us understand it. So what is conditional probability? Conditional probability is something like you have, you know the effect, right? And you now know the cause. There is two probabilities: the probability of occurring of an event and the probability of why the event occurred. Now, if I give you that the event has already occurred, and now the reason for why it has occurred, if I ask you, that is a conditional probability. So it is conditioning on a particular event that has already occurred, or I assume that it has occurred, right? So the formula goes like this. So for A and B, that there are two events. Now you have to get that event B that is there. So event B must lie in the sample space. So I think we have done it in the probability tutorials that if an event B is in the sample space, then it has some uh, probability greater than zero, right? So event B must lie in the sample space, and the probability that A given B is then written as probability A intersection with B divided by the probability of B. So here we haven't conditioned on the particular thing that A is in the sample space or not, and that is not at all likely for us to do it, because if A is not in the sample space, you can think that A intersection B would give you zero, and it is obviously zero. That is the probability of occurring of A given that B has already occurred. So you can understand the following terms. I have written the definition, that is probability A given B, and then it is a probability of A intersection B, that is probability of both A and B occurring, and the probability of B. Right. So now think of there is another theorem that we would require here, that is a law of total probability. So suppose that you have a sample space. Wait a minute. Let me just draw this thing. It would be better. Yeah. So suppose that you have given the sample space like this, and this is your sample space omega, and you partition it on different. You partition it like this, right? I tell you that this is B1, this event is B2, and like this it continues, and this is Bn, right? Finally, now I say you that so what is there is B1 and union B2, union dot 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 dot, and when you take on this union to Bn, that would give you the whole sample space, right? That is what we need. And the second thing is, if you see that there is no intersection between B1 and B2, right? The lines that I have drawn are parallel, or there is no same region or common region between B1 and B2. So Bi intersection with Bj is equals to phi. That is, there is no event that has occurred in B1 and B2. And obviously the B1 and Bi's must have the this must belong to the sample space, right? That is how you define a partition, right? A partition of a sample. Okay, so moving on, we have that partition of the set of the sample space, that is, we define different regions in the sample space, like B1, B2, and Bn, such that they are mutually exclusive. That is, there is no overlap between the two events, and then the union of everything, like you cover everything within the partitions, right? That is collectively exhaustive, and they have the positive probability of occurring, right? There is probability of Bi is greater than zero. Then after you have the following formula, like for an event and a partition, so you have that the probability of the event of occurring is just the summation of probability of A union Bi's, because you have divided the whole sample space into the regions of Bi, and now when you sum up on all of those samples, that would give you the whole A, right? So that is how you come up on the law of total probability. And now there is a very interesting theorem, that is the Bayes theorem. So Bayes theorem tells you how you can reverse the conditional probabilities. Like you are given the probability that a cause has occurred, like the earthquake has occurred, and you want the how many buildings have been destroyed, and you have that probability, right? And now you want to find out that the number of buildings that have been destroyed and the scale of earthquake that has occurred. So at that time, the Bayes probability is very helpful. Like you want to reverse the conditional probability, so it helps you in like this. So the Bayes probability has the following formula, that is probability of A given B is equals to probability of B given A times the probability of A divided by the probability of B, right? So that is just so the proof is very similar. Like the probability of A union A intersection B is equal to the probability of B intersection A. So you divide it into you write it in similar terms and then you swap with the terms like that. So now let's move on to how effective the strategy is, right? So let's be precise about our problem. We define it very cartoon character way. So suppose that BR is an event that we successfully select the best candidate using the threshold of R, right? So I define that event to be BR. And now I define AK to be the event that the best candidate appears in position K. So observe that the probability of BR and AK that is there. So that depends on each other. Like you successfully select the best candidate using the threshold R, and the position of the best candidate is at K. So if R is less than K, right? So then you have a probability of choosing the best candidate. But if R is greater than K, then you have rejected the best candidate, so you don't have that probability, right? That is zero. So now since all orderings are equally likely, the probability that the best candidate appears in the position K is probability of AK is equals to 1 by n for all K, right? Now I say that this is a theorem that is the result for us. That is the probability that there are n candidates and you have to select, you have a threshold of R, then the probability of selecting the best candidate is R by n times the summation of j equal to R to n minus 1 of 1 by j, right? So so the proof goes like this, that is using the law of total probability, the probability of BR, that is you have selected the best candidate using the threshold of R, is basically the summation of k equal to 1 to n, and you divide the whole range into different partitions, that is AK. So we could do this because of the conditions that AK, so the for best candidate that is there, he must appear at some position, right? So you can take him to be at position 1, you can take him to be at position 2, and so on up to n. And the he cannot occur at two different positions at the same time, right? So there is no overlap too, and he has to occur. So there is a positive probability of occurring at some position or the other. So we can apply the law of total probability here. And if you think about it, so the probability of BR is that probability BR given AK times the probability of AK, and you sum it up for k equal to 1 to n. So then the key insights that are there, that is if k is less than R, so then you reject the best candidate, right? You have already rejected the best candidate. Or if it even if it is equal to, sorry, even if it is equal to, you have already rejected because the first R candidates are to be rejected. So now if k is greater than R, the success occurs if the best among the first k minus 1 candidates, because and the is in the position 1 to R. Why is it so? It is because, think about it, if there is any other candidate in between R plus 1 to k minus 1 who is better than the best among 1 to R, she must have selected that candidate first, right? So there is no probability that she would go to the kth participant, right? That becomes zero. But we want her to land up to the kth participant, that is the superhero guy. So the success occurs when the best among the first k minus 1 candidates is in the position 1 to R. Now that probability is just R divided by k minus 1, because you have R positions to position the best among the first k minus 1, and you have total k minus 1 places. So that is a simple combinatorial problem. So if you think about it, the probability becomes R divided by k minus 1. Now you know that probability of BR given AK, right? And you know the probability of AK. So you just do the multiplication and then you sum it up. So what happens is R divided by k minus 1 times 1 by n, that is the probability of AK. And you take out that R and n, the numerator and denominator, and you replace k minus 1 with j, that is, you replace that and you get the summation symbols to be changed, and j comes from R to n minus 1. So if you think about how this, like we wanted to find the best approximation for R such that she gets to land up on a higher probability, right, of choosing the superhero. So if you think the probability looks like something like this, that approximate plot of P and K looks something like this, and you see the maximum occurs at somewhere between 0.3 to 0.4, and that is she gets a maximum at that point, and it is somewhere between 20 to 30, the range where among the 100 candidates, the number of candidates that she rejects if the R value, so that R value is in between 20 to 30. So if we think about it, if we do some plotting and on GeoGebra or Desmos, so you would get that the maxima occurs at n by e, right? Now, for those who know a bit of calculus, so the summation can be approximated by integrals, right? So the PR can be approximated as PR by capital N, where capital N is the number of uh, candidates that are there, and you have to take the N to be large enough. So you get the PR to be equal to R by N times the integral of R to N 1 by X dx. So 1 by X dx is basically ln of X, and ln of X, that when done with the limits as R and N, so that would come out to be ln of N by R, right? And you put the value of R by N to be X, and then you find a function that is fx that is equal to X times ln X, and then you can replace ln of X by ln of 1 by X by minus of ln X, and then you differentiate, that is taking the derivative because you want to find the derivative and put it equal to 0. So you differentiate it and get it as minus ln X minus 1. It is a easy calculation if you think, and then setting it to 0, we get that the value of X to be equal to 1 by E, right? So therefore she must so now X equal to 1 by E would imply that she has to select R to be equal to N by E, right? And that implies that the probability is approximately equal to, if you put it again back to this equation, this following set of equation, that is R by N times ln of N by R. So if you put it back there, you would get that the value of probability turns out to be approximately 1 by E, that is 0.368, right? So if you see the graph, how it looks like, is it optimal or is it very bad or something? So the probability of selecting the best candidate is somewhere like this. The graph looks like this, depending on the number of candidates that she chooses, right? The success probability versus the number of candidates. So if you see that the probability is high in the beginning and then it comes closer and closer, closer and closer to 1 by E as n becomes larger. And when n is approximately 100, it is almost 0.368. That is 1 by the probability of selecting the best one. So surprisingly, this is a very great method as such as given by Shinchan. So Miss Nanako can achieve a constant value, like for a very large n, can achieve a very high probability, that is 36.8% of probability of selecting the best price. Whereas if we had gone by the selection of randomly selecting anyone, you would have landed with 1% of selection chance, right? So that is a very high probability of landing. Now, this is known as a famous secretary problem, which is used in optimal stopping theory. It has a lot of applications, like you can, for as the name suggests, right? So secretary problem is used in hiring a secretary or a particular candidate as in your job or something. You can also use it for dating purposes, university admissions. Universities use slight variations of this secretary problem to, like, when the n. So the major advantage of this question was that you had the particular n given to you, right? But suppose that the n is not given to you, it becomes a bit more tedious. So at that time, the universities use that kind of strategies to select the best candidate among all the CVs or resumes that you sub. So it's also a random process if you think about it. So what if we use n by 2 instead of like, we can't use n by e, right? Uh, so you need to some integer values or something right there. So what happens if we use n by 2? So n by 2, that is 50% strategy, would lead you to 28% success rate, whereas n by 3, that is almost gives you a very high success rate, that is 33% success rate. But the lower you go or the higher you go, that is the more candidates you reject or the less number of candidates that you reject, the success probability decreases, right? Because we had already found out that the maximum occurs at somewhere at n by, wait, where was it? Yeah. So the maximum occurs at somewhere n by e, right? Near to that n by. So the more you choose accurate to that n by e, the higher probability you get on landing to the superhero guy. So moving on, there are real world applications of early decisions, or when to accept an offer or when to reject it, or something like how many job interviews to attend, when to accept a job offer, house hunting, how many houses to view. Like when you pick a house for yourself, like when you grow up, you have to pick a house. You want to view each and every house, which is the best house, but obviously you can't. Then you use the strategy to get a perfect house for yourself. So you look at n by e, so the summary, like ending section of the presentation. So you look at first n by e options of uh, the given whole sample set, and then you get a 37% probability, and better than random choices, right? Obviously, that is 1% success rate. It is very high. 37 is very high than one, and it works in many situations. It is not like an ideal thing that you can think about, but it works. It almost works. So how will you use this strategy in your life? Is like you want to pick an ice cream shop. At that time, you can use this strategies or something. Or you want to pick a perfect item for yourself. You can use this strategy. So this is a kind of a uh, just a joke for you. So the two persons talk about the strategy that is there. That is, so will you go out with me and blah blah blah. So mathematics is a bit difficult, but it works. And remember that the best decisions is not about finding the perfect options, but about making the best choice with the information that we have. So that is how optimal decisions help you to find the best with the limited information that we have. So are there any questions that you would like to ask or something?
Sir, can you please show the comic slide once?
Okay, wait. Okay, now we can also go on with the rain problem that was there. So how do you think about the rain problem? Like, how do you think you can solve it? Like, you have seen one problem, right? So give me your ideas. How do you think you can solve that rain problem?
Well, like we can do like we know the number of days it rained continuously, so we can
Yeah,
use the same strategy. We can the number of days it rained continuously, we can divide that by e, and then we can wait for that number of days to conduct the party.
but you don't know the number of days you want. Like, you don't have a here. What you had is a fixed number of days.
No,
That
no,
is a
we know the
fixed
previous
number.
data. No, that how many number of days it rained before the previous data we know. No,
Yeah, that
so
is
we
it. But
can
uh,
use that.
here what you had is you had to select a particular day in the future. Like if you think about the secretary problem or the marriage problem, so you had something in the future, right? Like you had to select someone from the future, and but here it is like you have the past information and you want to translate it to the future. Like you want to know when it would rain or how it would vary in the process. Like which day would have a higher probability of raining, given that it has rained for the past 10 days. So that comes out to, wait a minute. Let me just turn it. So is my screen visible right now also? Just to confirm.
Yes, yes, it's visible.
So if you think about that, that turns out to be, so suppose that you have been raining. It has been raining for the past m days, right? You know that it has been raining for the past m days, and you are somewhere here in the present, and now you want to predict somewhere in the future where you want to organize a party, right? You want to organize a party the next day. What is the probability that it rains the next day, right? So suppose that I ask you the probability of raining on a particular day in the future. That is what we want, right? That is what we want to calculate. Now, each day is an independent day. First of all, that is one thing that is to be made sure. Wait. Each day is independent, right? And so the probability that it rains on a particular day, that is, let's say it rains on the jth day from the present, it rains on the jth day, given that it has rained for the past m days, right? For the past m days, it has rained. It has been raining. Wait a minute. Yeah, that is basically the probability of intersection of the two events. That is the past m days divided by the probability that it has been raining for the past days, right? So that is the conditional probability statement that we had. Now think about it. So you have taken the jth day to be your particular day. That means that it has been raining for the past m plus j minus 1 days, right? It has been raining for that. If you have chosen the j day as your particular day of event, so that gives you the number of days it has rained. So that is m plus j minus 1 divided by the total number of days that were there, that is m plus j, divided by the probability that it has rained for the past m days, like you know the past that is there, right? So the probability is 1 for that, like you know that it has rained for the past m days, right? So that is m plus j minus 1 divided by m plus j. Now from here you can take this to be you can take m plus j to be equals to k some value, and then you can approximate this probability as k minus 1 by k, right? Now that is just equals to 1 minus 1 by k. Now you can take it to be a function of k, and then you differentiate it. So that is something a bit non-trivial, right? Like k turns out to be infinity, right? So you
But
the
here
more you
we, but here we assume like that the number of days we waited j, so it would rain each day.
yeah, it could rain. The rain is independent of every day, right? It could rain today also. It could rain 5 days later also. It's like a Bernoulli process. Like a Bernoulli process is something like it has a probability of p occurring and a probability of 1 minus p of not occurring. There are two conditions, and that's all. Like you don't have any uh, conditional probability. Like it is independent of each day. Each day is an independent day. So then what happens is, if you think so, the more later you choose the day, the that is the best day, right? But you don't want to, right? So you want a perfect day. So that tells you that mathematically you can't have a day such that it does not have such that the probability of raining is 0. But what you can do is you can you can calculate this probability out, this particular term, and then when it is less than some particular event, like you know that, wait a minute, yeah, when it is less than 30% or something, you fix that day to be the best day for your picnic or something, because less than 30% would imply that the probability of raining is very low, right? Because it is just 3 by 10% of 3 by 10. The probability of raining is 3 by 10. So, so that is how you can think about the problem. Like now, when n is very large, you can think about it differently. Where am I? you can think about it differently. Like when it is the value of n is large, you can do one thing. It is you can read about Laplace law of successions where it is a so I could not do that Laplace law of succession here because that requires some Laplace's law of successions. So that tells you how much probability is given that the particular event has occurred in the past for a number of times. So you tell me in the future how many times it can occur more. What is the probability that it occurs again in the future? So then there is the Copernican principle. These are something that you can read about uh, right now. Like you have that idea after this lecture of how we can do that. Copernican principle. That is Copernican principle is something like it has what Copernicus did is uh, he said that it has been the sun has been shining for particular m days in the past, and I want to calculate the probability that the sun shines tomorrow again. So he was something like of a different, a bit logical thinker. He didn't believe in the absolute truth. So he said that let me calculate the probability of sun again rising on the jth day, or so that is Copernican principle, and he did that, and that is all about today's meeting. So is there any other question that you would like to ask or something about probability that you would like to discuss? Any questions or something?
So, is there any more question? Maybe we can wait 1 or 2 more minutes. One has any question, and ask. After that, we'll stop. So for the participants, the next talk will start at 2 on Carmichael numbers and primary testing. Maybe we can stop here. Yeah. Yesterday's recording and slide will be mailed. So, oh no, not the tutorials. Actually, we won't upload the tutorials on YouTube. Maybe we will share from the Google Drive wherever we have. But just Shubhajit, someone has question about some infinity.
Yeah, I didn't understand the question particularly. Like, what do you mean by infinite number of coins or something? Acha, we need infinite heads. What is the problem? So, look, if you think about it, the probability that infinite number of heads is basically half to the power. Like, if you want an unbiased coin, then it is half to the power n, right? The probability of n number of heads. And then when n tends to infinity, that half is less than 1. So it would obviously tend to 0 when n goes very large. So something like that. But if you want to calculate something like the probability that there were m number of coins that were coming up heads, and you want the m plus 1th coin to come up head, that would again be half, right? And when n tends to infinity, that would also be half. Like there are infinite number of coins that were heads, and you want the infinity plus 1 or something larger infinity to be also head. So then that is something conditional probability tells.
Okay, any more question? Okay. So next up we'll start at 2. See you. We'll end it here. Thank you everyone for joining. Thank you Subhojit for the talk.